Okay, let's continue. We identified the material plane initially perpendicular to the midplane location after the two rotation phi x, phi y that we had. Now, when I prepared this so we can go a little bit faster on this. So this is, the location, let's say xy that we are considering uh, at the located point in the midplane. We have two tangent to this location along these two different curves in x and y direction. And we can say that if we consider the vector location x, y, and w, therefore we can write the tangent for the deflected midplane at the x along the x axis is given by this relation. And if I simply apply this to R, then it will become 1, 0, and W. Note that W is not a function of Z, it's only a function of X and Y. So we have to keep the partial derivative. This is contrary to the beam theory that we could drop the partial differentiation and use total derivative. Similarly, for the y direction, we differentiate this with respect to y. So this becomes 0, 1, and dw dy. Now, this is the important part. This is the connection between so-called geometry that we derived here. Maybe I change my pen color to black. This is pure geometry, this relationship that we have for rotated material plane initially perpendicular to the midplane. But now we have to satisfy this part, the perpendicularity to deflected midplane. In order to do that, we come here and say, okay, these two vectors are the vectors along the tangent. So if I find the cross product of this vector, it will be a vector perpendicular to that location at the midplane. And exactly this is what I want. And this vector should be aligned with the plane, with the direction of the deflected material line that we have calculated. So mathematically what we need to do is to find the cross product of these two, which you can use the determinant process. So ijk here is the unit vector about x and y and z. And the first one is 1, 0, w dw dx. And second one is 0, 1 dw dy. And if you work out this determinant, you will get this result. Now, if you make this equal to the material line, which they should align, you can conclude that I missed a Z here, maybe. I put a Z. You can put the Z at the end so we don't miss it here and there. So this will become, phi y becomes minus Z, sorry, this shouldn't be. Okay, I do the Z at the end, so not to confuse it. So if you put these things together, then you will get that phi y phi y is minus phi x, and phi x is equal to phi y. There is no minus here. And correct. So this relationship is correct. Now, if you come and say, okay, a general ux, uy, displacement in x direction, y direction, and z direction, and work out the relationship between these two. The z comes in. So u is the displacement of a given x, y, z point in the x direction, v is in the y direction, and w is in the z direction. So any x and y, they will not move away. Any given x and y point, it will exactly deflected in this z direction the same way. Okay, so once I have my displacement, I can easily move to strain tensor. And for linear, because these are small deflection, we have here I and j is 1, 2, and 3. And so this is say x 1, z 3, and y 2. Okay, coordinates. Okay, so I work out the couple, and then you see what's happening. Eij is equal to, we have to have our displacement handy. So this is by du dx 2 times. So 2 times 1 over 2 goes away, cancel out, and then I get minus a z, because differentiation is with respect to x. I get my first strain or normal to x to the plane at the normal to the x direction. This is my first strain or normal strain. The second one becomes minus z d2w dx dy. The third one goes 0, and it is easy to see this because this is 1, 3. So I is 1, j is 3. So du d3 is dw dx. I wrote it here. So 1, 3 here is du d3. So it is du dz plus du3 d1. So it is dw dx. But du dz is from here is minus dw dx. And dw dx is dw dx. And this cancels out. This is the way to calculate these things. It is symmetric. So symmetric. E21 is equal to E12, and the diagonal EYY becomes D2W or omega. I guess I call it W because we mentioned W, and then this is 0, and then let's call it 0, 0, and 0. So this is Kirchhoff-Love plate theory strain tensor. Okay, there are several important things here, and that is maybe call it here. First of all, these shear stresses are 0, shear strains are 0, and obviously these two. So if you come here and look at what are these actually is this, that I draw intentionally thick plate element here to show things, but actually it is thin. So this is EXX, this is EXY. Similarly, this one, this is EYY, and maybe change color here. And this is EXZ, which is 0 here, meaning there is no shear across the depth based on the assumptions that uh, Kirchhoff-Love implies. These are the assumptions. Based on these assumptions, we have worked out systematically and rigorously the kinematics and the displacement field, and the strain field. Shear strain is absent, at least one of them, the red one. The other one, which is EXY, which is this one, is not. So what does this mean? It means that the KL plate theory ignores transverse shear strength, which immediately signals that there is something missing here. We know that the plate will develop shear, across along the depth, and it is needed for equilibrium. So we will get to that. Another thing is that the changing color sometimes takes more time than it is. So this is also 0. I'm referring to our, assumed coordinate system that's shown here, x, y, and z. Okay, and so now that's okay as long as we assume that these shear stresses are negligible, shall we say, because of the thinness of the plate compared to other dimensions. We can say that we can ignore that the magnitude of this shear in their effects into deflection. That's one thing. Second is that we cannot ignore them because of requirement for equilibrium, that we will get to it later. So one can come here and say that in a way we can actually consider a 2D plane strain, because every other element is 0. So in the green box, we can say that we have a situation that it is like plane strain. All other strains about the third dimension, which is z, is 0. So this is EXX, this is EXY, EYX, which is EXY, and EYY. So this is one thing that we can say. Okay, so far so good. Let's move to the stress. Call it sigma ij, which is lambda delta ij ekk plus 2 mu eij. I can write these things in terms of modulus of elasticity and Poisson ratio, I can write this as E mu divided by 1 plus mu, 1 minus 2 mu, delta ij ekk. Ekk is the trace of the strain tensor, sum of the diagonal elements, and then E divided by 1 plus mu EIJ. Sometimes we use the lambda and mu, if you recall, are Lame's constant, but more physical, meaningful constants are modulus of elasticity E and Poisson ratio mu. So if I come here and write it, write my stress tensor, and I will do some symbol contraction here. So d2 dx2 will be write it like this here and there, and d2 dy2 will be written as yy, etc. here and there. So I exchange between these two. So if you do that, you will get your normal stress as 1 minus mu divided by 1 plus mu, 1 minus 2 mu, w comma xx. This is d2w dx square plus wyy divided by 1 plus mu. And the next one is w comma yy, 1 plus mu and 0. This is, I don't write it again here, symmetry, meaning sigma 2 1 or sigma yx is equal to sigma 1 2 or sigma xy. This one is similar to 1 1, except you have to, there's a bracket missing here, 1 minus mu wyy divided by the same denominator and then w comma xx divided by 1 plus mu, and then 0, and symmetry again, and symmetry again. And third one is the interesting one. So this is del square and del square is, of course, we have a minus ze here for completeness. Remember the z that we dropped and picked up, it shows up here. Now del square, note del square is d2 dx square plus d2 dy square. I use that notation. So it is basically not z, because z is, if you write z, it is, I mean, it is 0 because w is not a function of z. Okay, so that's good enough here. W. So note that. Okay, so this tells us maybe I change color here again. We note here that sigma xz and sigma yz are 0, these two. But sigma zz is not 0. If I made a mistake here, this is not shear, this is normal. These are shear. Sorry about that. Let me draw a small element here so to show these things consistently and correctly. And I don't change pen. Sometimes changing pen becomes confusing. This is sigma x. This is sigma y, and this is sigma zz. And these are the shear. Another one that I should point it out is this guy here, which is common to this one, which is 0. So we say that in this there is no shear across the depth. There is no shear. Xz and Yz are 0, and that could be also an issue. Not for this theory, but for the equilibrium, because we need this shear for equilibrium. It's very similar to the Euler-Bernoulli equation. So normal, back to this, normal stress is not 0 if 3D, let's say Hooke's law, is used, which is this relation between stress and strain. So what should we do? We have an inconsistency. One way of doing it is that we say that, okay, when we look at this, what do we see? We have a mu Poisson ratio, and we can say that, can we assume that the material has a mathematically 0 Poisson ratio, and therefore this will go away, and these guys become 1. These coefficients become 1, so we don't suffer. But this will go away, which become consistent. But physically, this resolution is not justifiable, because mu is not 0. Even if mu is half, 0.5, then this will blow up, because this will become 0. And therefore, playing with the physical coefficient mathematically becomes another issue, problematic. So that is not the right path to go. So we cannot just say, okay, we ignore this stress and move on. See what I'm saying? Because these guys are 0 by themselves, these two create some issue, but more seriously, this guy is more serious problem here. This one, because there is it says that this is not 0 according to this calculation, but we know that it is 0. I mean, if we don't have any traction on the surface of the plane, then this should be 0. So the source of the problem is coming from that if we consider the full 3D Hooke's law using our resulted strain tensor from the assumptions of the Kirchhoff-Love plate theory, we ran into an issue as an inconsistency. So we have to do something with this three-dimensionality, shall we say. In other words, we can say that geometrically and kinematically uh, things are okay, but from the elasticity or kinetics point of view, uh, we get something different because of this stress here. Okay, so the remedy number one was to play with the mu as a mathematical parameter, which didn't help us. Another way is that go back to the fundamental assumption. Maybe there is something here that we are imposing too much constraint on the behavior of the normal line to the midplane. And specifically, the midplane remaining normal to the deflected, this normal line to the midplane remains normal after deflection also. Maybe this is too much of a constraint. So that is the source of going from this theory to another higher level theory, shall we say, or higher order theory, uh, which is the basis for another video. I will not go to that, and that would be kind of mid-lane beam theory. Another one is that, so these are remedies that I'm discussing here and the problem that we ran into. And these are very important in terms of understanding these theories. At least for now, this is the Kirchhoff-Love theory that we use a lot in practice. So these are the inconsistency that we get. So we have to understand these things in order to truly understand what these theories are talking about. So another remedy is that considering a 2D kinetics. By that, I mean that we should come and make a two-dimensional version of this relationship. This is another way of looking at this. Which also justifies this point that we, in all of these three-dimensional to two-dimensional treatment that I mentioned at the beginning, we study the asymptotic behavior of all of these quantities in a kind of series expansion. So if you expand these quantities, basically we are taking care of them as the first term, and then we can go to second term and so on. If you have seen my video on ready or three-dimensional or third order shear deformation model for beams, you can have the same thing here, but we are not there yet. We are just at the level of the first term. So these remedies basically are possible. So we say that basically the justifiable one is to, maybe I keep the red here, to get a 2D. I will not call it plane stress for a purpose that I will explain. A 2D version of 3D Hooke's law. This is the remedy. On the background, we are assuming that we are keeping that assumption of H over R is small. So what is this? What is this? Again, I repeat here because it's important. Our strain tensor is consistent with all of the assumptions. So up to here, you don't have any inconsistency. Once you jump to the stress and use the three-dimensional Hooke's law, then you get some inconsistency. Now, what is that? Is that we say that we come here and integrate the 3D along the Z in general, symbolically. And therefore, we get a two-dimensional version of the 3D Hooke's law. This is based on the assumption that the variation in the Z direction is small compared to the this. So we integrate the whole thing along the Z, and therefore based on that we will get a two-dimensional version of the Hooke's law. If you like, and if you don't mind, uh, theories are kind of sometimes feel patchy. Means that you patch together things to get it, but they work. Amazingly, these things work because the assumption is not uh, falling from the skies. It is based on that asymptotic expansion um, of the quantities involved. So we would like to do this in in this KL beam theory. Okay, so if we do that, then I write here, so the constitutive equations two-dimensional version of Hooke's law. If you like, kind of quote-unquote plane stress problem. So here the assumption is okay, the assumption, sorry, my pen lost connection. Assumptions is this, that sigma xz equal to sigma yz equal to sigma zz is 0, which is, if compare this assumption to our strain tensor, that is these three elements here which are 0 and the corresponding symmetric one. But if we get our stress, as I mentioned, from a fully 3D treatment, then these two are 0, but the ZZ is not 0. These two are 0 by itself is a problem because we ignore shear effect on deflection. You may accept this, say, okay, that's small, but this one is a problem because this is normal stress and we cannot have it if we don't have traction on a plane on a plate surface. Okay, so once you do that, then you come here and say, how do we get that? There are several ways of doing it, but I do it, I think, in a very more direct way. If you have a, let's say, an element, say x and y, say, just on the side note, and then you apply some stress in the x direction, and then you get the same element and you apply some stress in the y direction. So you see here that if I write epsilon x according to Hooke's law, this will be sigma x over E, modulus of elasticity. But if I want to include the two-dimensionality and using Poisson ratio, if I stretch this element on the top in the x direction and y direction, y will want to bring it back because of this effect here, the Poisson effect. So I have to subtract the mu fraction of sigma y over E. Similarly, this is EY is sigma y over E minus mu over E sigma x. Okay, and these are two-dimensional. You can also say that 2x exy, I use gamma here, gamma xy on the side. Now, if you come here and eliminate, actually solve for a sigma x and sigma y, solve for sigma x and sigma y, you get sigma x is equal to E divided by 1 mu square Ex plus mu Ey, and sigma y is the same ratio here, coefficient, at Ey plus mu Ex. And obviously tau xy is 2g. Exyg is shear modulus of elasticity. You can write it in terms of E and mu like this. So these are my 2D plane stress or plane stress Hooke's law relationship between stress and strain. And if I use this, then using Eij calculated, by calculated I mean the Eij that we got here in terms of W, we get Eij is equal to d2W dx square plus mu d2W dy square, and sorry, this should be not Eij but sigma ij. This would be d2W dx dy. This is symmetry, meaning sigma 2 1 or x yx is equal to sigma xy, and sigma yy would be of course there is a coefficient of z e divided by 1 minus mu square to the whole thing. So this is, let me box it, this is Kirchhoff-Love plate theory stress tensor. Okay, and we see here that it is consistent with our boundary condition requirement. So if you don't have traction, then this stress sigma zz is 0, and then we have a 2D, two-dimensional. So the point again here is that you cannot take it from this and say, okay, I get this. You get some coefficients of these each elements here wrongfully. Second, as this ignoring this on the surface is not justifiable unless you integrate through the thickness, and I will do that later, through the thickness, and then say, okay, let's go to 2D, and then with 2D you get the correct one, the correct stresses. If I want to kind of give you a quick summary of what we have done so far in relation to KL theory, is that we came a summary maybe. So we get the geometry phi x phi y, then we get the KL assumptions, all of these theories have some assumptions. And the key here is that once you imply these assumptions or impose these assumptions to your kinematics should also comply or be justifiable. Sometimes this problem is not easy, and if you get a very constrained assumptions in the geometry, then your kinetics will suffer. And if you relax this, the whole thing becomes complicated. And that is the dilemma that we have in both beam theories and plate theories, both of them. Okay, so from here you go to active rotation. We went to active rotation. Active rotation. Then we got our displacement. Then we got to, maybe I write it from right to left, to our strain. And up to this point, we are consistent. The theory will not suffer any inconsistency. But after that, maybe I change color here again to red. After that, you run into inconsistency if you go 3D. But then you say, okay, 2D version of elasticity. And 2D version, 2D plane stress, say plane stress. But this plane stress is not the plane stress that we usually refer to, that is saying, okay, everything is two-dimensional. No, we have integrated in third dimension in the z coordinates direction to get into our two-dimensional. So there is another patch here that we have to introduce to make sure things are good. And that is maybe I say by integration along z, the depth, and then integration of 3D equation, and then we plug in strains, and then we get to our final governing equation, which I'm going to cover it so. Okay, so this should complete this video. In the next video, I will go to the equilibrium equations and then use the results that we have. This completes the Kirchhoff-Love plate theory as far as this theory is concerned. The first two videos, some background, that I explained, and this video goes to the relationship between kinetics and kinematics, and point out some dilemmas, some discrepancy that we get in this theory, and then how to resolve this discrepancy, and then finally how to get to our stress tensor. Thank you.